It's dusk in the void of space, and you're hurtling toward one of the universe's most mysterious objects, a black hole. Time stretches, light bends, reality itself begins to flicker. What if I told you that near a black hole, time itself can warp, that minutes might stretch into years depending on where you are? This isn't sci-fi speculation. It's the eerie reality predicted by general relativity, manifested in the immense gravity wells known as black holes. You imagine yourself floating near the horizon of a black hole. To you, your watch ticks normally, but back home, people would see your seconds stretch into hours. That's gravitational time dilation. The stronger the gravity, the slower time passes for you compared with someone farther away. Here's the problem. These aren't just fascinating thought experiments. They challenge our deepest intuitions about time, cause head-scratching paradoxes for explorers of gravity, and force us to rethink what now means in the universe. What does it mean to age, to travel, to observe, when gravity warps time itself? Let's break it down. Gravity isn't just a force. Massive objects warp the fabric of space-time. A black hole is an extreme example. Its gravity is so intense that space-time is curved to such a degree that even light cannot escape. Time dilation near a black hole is not one of those tiny corrections you'll feel on Earth. It grows extreme. According to calculations, at just a little above the event horizon, the dilation factor becomes enormous. For example, at 1.2 times the Schwarzschild radius, a day near the black hole might appear as 2.5 days to someone far away. At 1,005 times that radius, a 24-hour stay might equal 141 days elsewhere. What this means: if you ventured near the black hole's edge and then returned to Earth, you might come back to find years have passed while you barely aged. From your perspective, your time was normal. But for those far away, your clock appears frozen, your image redshifted, and your arrival delayed. Now, from an observer far away, something falling into the black hole seems to slow down, dim, fade toward a standstill as it approaches the horizon. It never seems to cross from their vantage point. That's a consequence of how time and space stretch and squeeze in extreme gravity. So what's the solution? Or at least the takeaway? First, this phenomenon gives us a profound window into nature's laws. It confirms predictions of general relativity that gravity can influence time. It means that if we ever build technology to approach such extremes, we must account for time distortion. More practically, it reminds us that our everyday experience of time is not universal. It is shaped by our position, velocity, and the gravity around us. Second, for scientists, this means studying black holes is more than watching light disappear. It's about observing how time behaves under extremes. Every new observation of a black hole, every measurement of gravitational waves, helps refine those theories. Third, for you and me, it invites awe and humility. Time isn't an immutable constant. It's malleable under nature's greatest forces. If you find a place in the universe where gravity warps time, you've found a place where the future can be compressed, the past stretched, and the present reimagined. In the end, black holes don't just swallow matter. They bend time, twist our sense of reality, and challenge what we assume about the ticking clock of existence. So next time you glance at your watch, remember, somewhere in the universe, time might be doing something very different, very slowly, very strangely, and that something is beautifully real.